All right, what's up, everybody? Welcome to the next video. Um, First of all, I want to say thank you guys so much for doing a great job with that activity on Monday and Tuesday. That's one of my favorite things to do in class, and so I'm glad that we were able to make it work in a virtual setting. I know I've also posted a follow-up video for you guys to watch, so this video today is going to be relatively short, all right? I do want you to watch this prior to coming to class Thursday and Friday, all right? So let's get into it here. We're going to be talking about periodic trends, and I'm actually going to be breaking this topic up into sort of two different days, okay? So like I said, this video is going to be relatively short. The next one, which you'll watch over the weekend sometime probably, will be a bit longer, okay? So for today, what we're going to be talking about is this right here, Coulomb's law, okay? So the overall objective for the lesson is for you to be able to use Coulomb's law to explain periodic trends, okay? And later in the second video, you'll be learning about atomic radius and ionization energy and how the periodic trend for those things work. For today, we're pretty much just going to be worried about this thing called Coulomb's law, okay? And we're going to do a virtual like lab simulation thing with Coulomb's law. It's not as cool as it sounds, okay? So lower your expectations, okay? But it is kind of neat. We're going to be doing a little bit of like a virtual simulation thing with Coulomb's law in class on Friday, or Thursday and Friday. So this video is really all about just Coulomb's law, okay? Because it is very, very important when it comes to periodic trends. So what is Coulomb's law? Coulomb's law, well, here it is over here, okay? Coulomb's law is a mathematical expression, or formula, you could say, that can help us understand the behavior of subatomic particles inside of atoms, okay? So let me put this into some perspective for you, all right? This unit on atomic structure has been all about like what is inside of atoms, right? First thing we talked about was protons, neutrons, and electrons. We talked about isotopes, how they can have different numbers of neutrons. We learned how to calculate average atomic masses of different isotopes. Then we got into electrons and where they are, electron configuration. We sort of applied electron configuration to learn about the shape of the periodic table. And now what we are doing is we're going to be learning about how protons and electrons specifically behave. Okay, how do they act inside of an atom? All right, so we are sort of wrapping things up in Unit 2. We're getting towards the end of Unit 2, okay? And so after this, we're going to be able to talk about how atoms interact with each other now that we know everything about what atoms are made of and how they behave, right? So a little bit of review here. Protons are positively charged particles, right? And electrons are negatively charged particles. They are charged particles, okay? Coulomb's law tells us how charged particles behave and how they interact with one another, okay? You guys probably know this, and I think we've talked about this before. If you have two charges that are the same type of charge, positive and positive, or negative and negative, they repel, right? But if you have a positive and a negative, right, opposite charges, they attract, okay? Coulomb's law tells us how big the attraction is, or how small the attraction is, based on a number of factors, okay? So let's just look at a few scenarios here, okay? Oh yeah, that's right. I forgot. I have to go through and tell you what these terms mean. Sorry, my bad. So yeah, Coulomb's law generally tells us the magnitude of attraction between charged particles, protons and electrons, and it depends on two key factors. Okay. So let's look at the formula here. F stands for the electric force, or the electrostatic force of attraction or repulsion, right? Depending on what you've got. K is a constant. We are never going to have to worry about this, not in this class, okay? Maybe in AP Chemistry. Q1 and Q2 are the charges, okay? And these are numerical values, all right? So for example, a proton, we would use +1, right? Or an electron, we would use -1, all right? It really is sort of that simple. And then R is the distance between them, okay, the distance between the proton and the electron, or the distance between the charged particles, okay? So, the way that protons and electrons behave, specifically electrons, the way that electrons behave inside of an atom is dependent on two key factors. The magnitude of the charge in the nucleus, so like the charge, right, Q1 or Q2, whichever one you assign to be the protons, and then the distance between the nucleus and the electrons, okay? Those two factors will govern how the electrons behave, or how a specific electron that you're looking at, how it behaves, okay? So let's get into some examples here and take a look at how Coulomb's law really works, all right? So let's imagine that we have two scenarios here. We've got scenario 1 where we have Q1 being +1. So think of this blue sphere here as being a proton, right, +1. And then Q2 is equal to -1. So think of this smaller sphere over here as being an electron, okay? So proton and electron, right? Now think of scenario 2, where Q1 is equal to +2. So this now represents two protons, okay, +2. Q2 still equals -1. All right, so this is still just an electron, okay? Let's assume that R, or the distance between them, is the same, okay? We'll just say that it's equal to 1. Doesn't really matter. Let's just assume that it's the same in both scenarios, okay? So the question is, in which scenario is the magnitude of the force of attraction between them greater? Okay? In which scenario is the magnitude of the force of attraction between these greater? I'll let you think about it for a second. Scenario 1 or scenario 2? Well, if you don't know, or if you're not sure, let's take a look at this formula, okay? The force of attraction is equal to, or based on, the product of the charges divided by the square of the distance between them, okay? So let's actually look at the math, all right? In scenario 1, we have Q1 and Q2, +1, -1, divided by the distance squared, okay? This ends up just being -1, okay? Notice how I haven't included K. We really don't have to worry about it. We're comparing these two scenarios, so it doesn't really matter what the value of K is, so I'm not even bothering to talk about it. Okay, so there you go. There's scenario 1. In scenario 2, Q1 is larger, right? It's got +2 instead of +1, right? 2 protons instead of 1. So we end up with an answer of -2, right? Because everything else is the same here. So which of these is the greater force of attraction? What do you think? Well, if you think about these numbers in terms of like a number line, technically this is like the larger number, right? Because this is like closer to 0, so it's like closer to being positive, I guess. But that's actually not how you should think of it, okay? We're just concerned with the magnitude of the force of attraction, okay? And in fact, this is a good opportunity for us to talk about what this minus sign really means. When you're talking about Coulomb's law and charged particles, the negative sign here just means that these two particles are attracted to one another, okay? This negative sign comes from the fact that these two charges have opposite signs, right? Positive and negative, right? Because a positive times a negative is a negative. If these were the same sign, right? Positive and positive, or negative and negative, then we would have a positive sign out here, right? So if your force is positive with Coulomb's law, that means that those particles are repelling away from each other. If your force is negative, that means that those particles are attracted to one another. Okay? Hopefully that makes some sense. So, don't really pay attention to the sign, right, for this question. Right? It just wants to know in which scenario is the magnitude of the force of attraction greater. The answer is scenario 2, right? If you have twice as much charge over here in Q1, then the force of attraction between them is twice as big. Okay? I think that makes sense. Let's look at another scenario. Okay? This time, the charges are the same. Okay, so Q1 and Q2 are +1 and -1 respectively in both scenarios. What I've changed are the distances between them. Okay? So in scenario 1, the distance between them is 1. And in the second scenario, the distance between them is 2. Okay, so I've like doubled the distance. So, in which scenario is the magnitude of the force of attraction greater? Scenario 1 or scenario 2? In which scenario do the particles feel a stronger attraction towards one another? Well, once again, we can just look at the math, okay? So plus 1 times minus 1 divided by 1 squared. So for scenario 1, we have a force that's equal to -1. In scenario 2, my distance has doubled, and I have to square it, right? So I get plus 1 times -1 divided by 4. So the magnitude of attraction here is 1/4 that it is in scenario 1, okay? So here, scenario 1 wins, right? These particles are closer to one another, therefore the amount of the force of attraction that they feel is greater than if they were farther apart, okay? That's how it works. Coincidentally, this formula for Coulomb's law is very similar to the formula that we use, it's very similar to the formula that applies to gravity, okay? The gravitational force is equal to some constant times m1 and m2, which is like the mass of the two things that you're looking at, divided by r squared, which is like the distance from the distance that you are from that object, right? So you can like calculate the force of gravity for a person standing on Earth or a person standing on the moon, right? And so it's the same type of principle, same type of equation that governs the gravitational force as well. Okay, so everything I just talked about can kind of be summarized in the context of atoms here in these two sentences, okay? With atoms, when the magnitude of the charge in the nucleus is larger, okay, so when you have more protons in a nucleus, the magnitude of attraction on the electrons is going to be bigger, okay? So if you have more protons, they are going to be attracting the electrons more strongly, okay? And vice versa, right? So if you had less protons, then the magnitude of force would be, or the magnitude of the attraction would be lower. However, when the distance between the nucleus and the electrons is larger, then the opposite happens, right? So when R gets bigger, the force actually goes down, right? So if you're comparing two different electrons, let's say this is my nucleus and you're comparing two different electrons that are further away are going to have, they're going to feel less of an attractive force to the nucleus than ones that are closer, okay? All right, I think that is pretty much all I need you to know for this video. Like I said, we're going to do a little bit of an activity with Coulomb's law in class on Thursday and Friday, and we'll get to the rest of the information on periodic trends in the next video. Okay, thanks for